let's look at Fischer projections. Fischer projections were developed while Emil Fischer was working with sugars. And sugars are molecules that have several asymmetric carbons within one molecule. And it's a little bit cumbersome to draw all of those asymmetric carbons. So he came up with a new notation or projection to indicate what each stereocenter looked like. And they've been kind of flattened out or projected onto the piece of paper. So here's an example. We draw the asymmetric carbon at the center of this like cross. And then we put our substituents around it. Like so. So this is a chiral molecule because it has 4 different groups around it. And the way that you read this is that structures or groups that are on the right and left are pointed up towards you, and structures top and bottom are pointed away. Always that is the orientation. So if I were to translate this into a wedge and dash notation, it would look like this. I have the fluorine pointed away, the hydrogen pointed away, and I have the chlorine and bromine pointed towards me. Now, I've got a model kit here that represents that. So here's the bromine, there's the chlorine, there's the hydrogen, and there's the fluorine. And you can notice how these are pointed towards us and those are pointed away. And if you look straight down this molecule, or at this center where this is pointed up, these 2 groups, the left and right groups, are pointed up, and the top and bottom groups are pointed down, that should match with what you're drawing for the Fischer projection. We're kind of just flattening out the molecule in this orientation. Now, if we were to rotate this by 90 degrees, we would actually get a different molecule, the enantiomer in this case. So I'm going to do that. So at the top now is going to be the bromine, like so. And if I write that in the wedge and dash notation, because now the fluorine is in the horizontal or kind of the left and right positions, that's where the wedges go. And now the bromines and the chlorine is below. That corresponds to this model right here. So you can see the hydrogen is now facing up, the fluorine is facing up, the bromine and chlorine are down. And this is the enantiomer of what we saw previously. So here's the previous one, and I'm going to align them with the Fischer drawing, right? So I've got them both lined up with what I drew on the paper. And now I will, again, just show, I'll rotate these around so that you can see they are mirror images of each other. So these are enantiomers. If you rotate a Fischer projection by 90 degrees, they will be the enantiomer. if you rotate it 180 degrees, then it's the same molecule because you've done two 90-degree rotations. So again, left and right, they always point up. Top and bottom, they always point down. So drawing something with just one stereocenter is not really what Fischer projections were made for. They were made for molecules that have more than one stereocenter. So let's draw a molecule in the wedge and dash notation, and then we'll convert it over to the Fischer projection. So here we have a chiral molecule. I've placed a methyl group on the third carbon, and I've placed a chlorine group on the second carbon. And now I'm going to translate this into a Fischer projection. This carbon, this methyl group, or carbon number 1, it's symmetrical. It is not a stereocenter. And also for these carbons back here, let's think of it as the ethyl, these two carbons, 4 and 5, they are also not chiral. And so they're not included the same way in the Fischer projection. So we'll just start at the top with carbon number 1, and we just write CH3 because there's no stereochemistry there. Then we come down and we draw the second carbon, third carbon, and both of these have stereochemistry on them, so they're included in this Fischer projection. Then we get down to this. Now we're back at non-stereochemistry containing part of the molecule. So we do that. Now, this is very helpful to have a model kit when we're looking at this. So I have one here. And I built it so that we have a methyl group that's going away from us. And we have a chlorine that's going towards us, just like in what I've drawn here. So now let's evaluate this from the Fischer projection. So I will orient this such as how I've drawn it here. So I'm putting the methyl group or the number 1 carbon up at the top, and I'm putting the others down at the bottom. And it's not important to orient it whichever way. This is just how I chose to do it. You could write the CH2, CH3 up at the top and the CH3 down here. It really doesn't matter. And now I come to this first carbon, and you can see that it's facing up, and it's on this, the chlorine's on the right side and the hydrogen's on the left side. So it's facing up and the chlorine's on the right side. So Cl goes here, hydrogen goes there. All right. Now here's where the potentially confusing part happens. This was facing up and it's on the right side. This, you would think, would go on the left side because, well, it's on the left side of the molecule here. But it's facing down. And Fischer projections only work when what you're drawing on here is always facing up. And in this zigzag configuration, this carbon is going to be facing up and that one's going to be facing down if you're just looking at a model kit like this. So what you have to do is turn it around so that now it's facing up when you look at the next carbon. This is why using a model kit is helpful. Now I can see that, oh, this is on the right side, just like the chlorine was. And the hydrogen's on the left side. So that may be difficult to see without the use of a model kit. And I understand it may be a little weird at first. Let's do another example, only in this case, we will translate a Fischer projection into our wedge and dash notation. Because we do need to be able to go both ways. So I've got a molecule that has 5 carbons. And I've got a chlorine that's here on the right side, a fluorine on the left, and a fluorine on the right. And then there's an alcohol down here. And we need to translate this into our wedge and dash notation. So I will just draw the backbone of this first. So we have an alcohol here. That's part of the non-stereocenter part of the molecule. 1, 2, 3, 4, 5. And so now we need to decide whether we should have wedges or dashes for each of these pieces. So again, I'm going to pull out a model kit here, and I will orient this with the alcohol down, just like I've drawn it here, and the methyl group is up here. And I'm going to check and make sure that I've made this model according to this Fischer projection. I have, but I'm going to talk you through it. So I have a chlorine, and it's on the right side of the molecule, and it's facing up. That's the first atom. And then I would need to turn the model over to look at the next atom. That's facing on the left side. So I've put the fluorine over here. That makes sense. And now I rotate it back up. And I have the fluorine on the right side, and it is facing up like it needs to. So I'm just verifying that I've made this model correctly according to this Fischer projection. Now I can draw my wedge and dash notation. So I will reorient this, kind of looking at it from the side so that I can get my wedge and dash. The alcohol is over here, right there. And you will notice that I've got the fluorine coming towards me, this fluorine coming towards me, and that chlorine coming towards me. So they're all coming towards me. So they all get wedges. Now you may ask yourself, wait, this is not that easy to determine, the wedge and dash notation from the Fischer projection. And I would tend to agree with you unless you've worked with these quite a bit and unless you're using model kits all the time to kind of do that translation. So you may ask yourself, what's the benefit of using a Fischer projection if it tends to potentially confuse you? So we have to kind of go back to what this was originally invented for, and that's sugars. And let's look at those. So I'll just draw some glucose over here in a Fischer projection. And sugars have a lot of stereocenters. And there's a lot of different combinations of them. And it could be difficult to keep track of it if you're looking at it in a wedge and dash notation. So I will draw the D-glucose variation of this. So notice how there's many stereocenters. There's 4 in this molecule. With that many stereocenters, there will be a lot of isomers, and it will be a little bit challenging or time-consuming to draw them all in a wedge and dash notation. Also, some sugars will tend to form rings, and then, do I draw it as a hexane ring, or, how do I want to do that? This is just another way. So let me draw the enantiomer of glucose, which is L-glucose, and I'll show you how this could be helpful, or maybe you'll see it as we continue on. So to draw the enantiomer, we flip all of the stereocenters, and so we can just draw the mirror image of this. And this is where the utility of it comes in, because it's easier to see the isomeric relationship of the different sugars, because you can easily identify which direction they are. So I noticed that all of these centers are flipped left and right, so this is now the L glucose. So the place that you will see these the most is in biochemistry when you're looking at sugars, particularly at sugars. Mostly because, again, it was developed to make drawing sugars and keeping track of all the isomers of them a little easier. And so this is where that really shows up. But you can use it for other molecules. So this is Fischer Projections. Thank you for joining me for this video, and we'll see you in the next one.